Okay, physics students, wherever you are, this is from what we did in class on Thursday, B2 day, Thursday, which would have been the 10th, Thursday, September 10th. So you were supposed to have made some data about rectangles, each of them consisting of 72 boxes. You were supposed to have done this. And again, I can only assume that you all are actually doing what I had asked you to do and keeping up with the videos. I've heard from none of you, so I don't know if anyone is actually even watching these and following along. But this is what your data should look like. Like there's a 1 by 72, there's a 2 by 36, there's a 3 by 24, there's a 4 by 18, a 6 by 12, and an 8 by 9. All of those are consisting of 72 boxes, and those are the different dimensions. And then you were supposed to have made a graph of width on the vertical and length on the horizontal, and that gave you this shape curve right here. Now, when you look up, well, hold on, before you even get to there, that's a curved line. We cannot write a y equals mx plus b for that line because it's curved. It doesn't have a slope. The slope is continually changing. So because it's an inverse curve like that, the slope is, I guess, inverse curve like this. The slope is changing. We don't have a y equals mx plus b because the m is not constant. We need the slope to be constant. And that brings up this term called linearization. If you look at the graphing summary sheet that I had posted, it shows you a list of the different graphing relationships. This is one of them. And it talks about being an inverse relationship. So that means for us that what we find out by looking at that graphic summary sheet, the width is what we call inversely proportional to the length, 1 over inverse of the length. So you could say that two different ways. You can either say that the width is inversely proportional to the length, or you can say that the width is directly proportional to the inverse of the length. They both mean the same thing. They're inversely proportional, or width is directly proportional to the inverse of the length. Now, on that graphic summary sheet, it tells you what to do to make the graph linear. That's called linearization. We are going to linearize the graph. We're going to make this curve not look curved anymore. We need it to look linear. So you need to do that. You need to look at that graphic summary sheet and make that graph not look curved anymore. We don't want it to look inverse. We want it to look linear. Now, how do you do that? Well, that sheet says to do this, to graph 1 over L. Graph 1 over L as your x variable, not L anymore, 1 over L. So 72 becomes 1 over 72. My goodness, what is 1 over 72? Well, it's small, okay? That's a very small value. 1 divided by 72 is 0.0138 or 14. So 0.014. That means your new length is going to be 0.014 boxes. That's the new 1 over L. And so you'd have a whole other column here. And now these would be 1 over L values. 1 over L. Now, that means you can't plot this graph on the same grid you just plotted your first graph. You're going to have to make a new graph, because if you're going by numbers that small, like out to the hundredths, then you might need to adjust your interval so that your graph is going by like hundredths. Like you could go maybe 2 boxes for every 100th or something to get you across, because your largest 1 over L value is then going to be what? Well, 1 over 9, which is 0.11 repeating, 0.1 repeating. So you have to get up to it like a tenth. So that's going to be small values. But that's what's going to go now on your 1 over L axis. So now it's no longer just L, it's 1 over L. And you have to convert all of these from lengths to 1 over lengths. And then plot your widths now with your new 1 over length variable. And that's called the linearized graph. And that should be linear then. And from that graph, you can then write an equation by finding a slope, looking at the y-intercept. So do that now. I'm going to continue to discuss what we talked about that day. So if you haven't done this yet, because I just now told you to, then you pause the video, do that, and then come back, and then I'll talk about what we had mentioned about this relationship. Now notice here, it does say, once you get this new graph, you need to find the slope, write the equation with units, and have a statement of relationship. Well, we already said the statement. The statement is that the width is what? Inversely proportional to the length. Or again, you could say width is directly proportional to the inverse of the length. Either one is correct. Pause the video, go make your linearized graph, find your slope, write your equation, and then start the video again. Okay, here we go. So this is what we found. Everybody did this, and then we got this. These are the equations of everybody that was in the room. Now we have width equals this times 1 over L plus 0 boxes. We have width equals this times 1 over L plus 0 boxes. And so again, that's the format that we see. Hopefully you have something, I guess, similar to these. These slopes, some of them are very close, 71.4, 70, 72, 72, 62.5. Those are all fairly close to each other. 50 is a little small compared to the others. 66.7, I suppose. I mean, that's closer to 70 than 62.5, but these slopes are fairly similar in value. Now, the question is then, what does that slope mean? Now, nobody had a unit on their slope. Oh gosh. Why are they doing this?
I do apologize for the interruption.
I have to pause.
Provide information to everyone.
I don't even know if it paused. Did it pause? I can't tell if it paused. I'm just going to keep going, I guess. Okay. Pay no attention to the man that's talking behind me. So nobody put a unit of measure on this. Oh my gosh. Seriously.
Please continue to send in your free reduced lunch applications so that when this extension ends, your status will be approved and ready to go. If you have charges from before September 14th, please make payment on your account. A la carte items and milk only will not be free under this program. Only meals will qualify. Will not be free for packers.
I don't even know if you can hear that very well on this or not. Maybe you can't even hear the speakers going on and on and on right now. Anyway, nobody had units of measure on this because they weren't sure what to do with it. Well, here's what happened. Your rise is in boxes. Your run is now in not boxes, but 1 over boxes. So your rise over your run is boxes over 1 over boxes. And so when you divide boxes by 1 over boxes, that means you have to multiply by the reciprocal of boxes times boxes over 1 now, which is now boxes squared. Oh, so if that's boxes squared, then what do you think the slope of this equation is representing? I hope you're thinking that slope now represents the area. What was constant of all of your rectangles? The area. They all had an area of 72 boxes. And you see then that your slopes are all similar to 70 or close to 72. A couple of exceptions, maybe. Hopefully you found yours to be close to 72. If you didn't, then maybe something got messed up along the way. Now, what else did I say? Oh, I wrote this out. I wrote out, okay, that means, hold on, let me move this. That means, let me get this out of the way. Your equation, the general equation of what you have here, if the slope is area, then W, or width, equals area times 1 over L. Well, that seems like kind of strange. So what I said then is I said, well, let's multiply both sides by L, and those cancel, right? And that puts L on the other side. And so what do you get? Well, you get length times width equals what? What do we call that? Area. So that is what you just discovered, that apparently the length and the width of a rectangle are inversely proportional to each other. All right? As one continues to increase in size, the other one is going to continue to decrease in size inversely with each other. Again, and that the product then of those is area. And that's what this equation is telling us. Now, this is not physics, okay? This is like data processing. This is how do you look at data and interpret it and figure out what it means. Now, I don't know if you all saw and understood and realized that the slope that you found after you found it was indeed supposed to be the 72, the area of all of your rectangles. Like in this case with the pi one, I'm assuming that you all, with around and across, knowing that that's circumference and that's diameter, it probably didn't take you long to figure out that the threes that you kept seeing for slopes here were representing pi. That one I think was fairly obvious. Maybe you didn't catch it. I don't know. But this one I think was maybe a little less obvious as to what that slope was trying to tell you, especially with the whole linearization thing. And it's just, that probably got confusing anyway. So what we're finding though is that slope represents area. And what you proved is that length times width is what we call area. That wasn't obvious though until you see that the unit of measure on that slope is boxes squared. And you know that something squared like that, a length dimension squared, is area. And so then you can put 2 and 2 together and realize, oh, that was supposed to be area. Anyway, one last thing here. We talked about the y-intercept. What do you think the y-intercept should mean or should be? It should probably be 0. Yours may not have been exactly 0, but it should be 0. The whole 1 over L thing, this is where we had kind of another conversation. With these equations, we said that if the across measurement was 0, that the around measurement should be 0 because you don't even have a circle, and that pi times 0 should equal 0. And you shouldn't have to add or subtract something out here, meaning that our y-intercept here was part of what we would call an error. So your measurements that you took weren't perfect, and there was some error in them. For these equations, if L is 0, if the length is 0, that's 1 divided by 0 times your slope. 1 divided by 0 is undefined. Undefined. So instead of 1 over 0, it would have to be 1 over infinity. As your length gets bigger and bigger and bigger to infinitely large, that's making 1 over L get closer to 0. And 0 times your area should equal 0. So in other words, as the length gets infinitely large, the width is going to get infinitely small, approaching 0. As L approaches infinity, width, W, is going to approach 0. That's telling us that as you have an infinitely large length for your rectangle, your width is going to be infinitely small, and you should not have a y-intercept over here. I don't know if that makes any sense or not. Like this group 3 here, they had 0.2. That means that your width can't be any smaller than 0.2. You could make your length millions and millions and millions of boxes long, but your width can only get as small as 0.2 boxes, because even if all of this stuff over here becomes 0, you still have to add 0.2 boxes to it, so your width can't be any smaller than that. Well, that doesn't make any sense. It should be able to be 0, approaching 0. So anyway, in this case, I think the y-intercept, it's safe to say that the y-intercept is also a indicator that we have some error in our measurements, or our graph as we put our, because there's no measurements here, it's just dimensions. The data was actually perfect. Your processing of it, plotting it, drawing a best fit, that wasn't necessarily perfect data. Now, that's pretty much it. What we did next is I showed them a pendulum. I put a little mass on a string, the string that everybody always asks me that's hanging over there on my desk, hanging down from the ceiling. I put a mass on that, and I started to swing it back and forth. And they started to describe some observations that they had of the pendulum. And that's kind of where we ended. And so next, so we looked at circles, we looked at rectangles. Now we're going to look at a pendulum and see what we can figure out about a pendulum. That'll be next. So I'm sure there'll be some more video coming out on Tuesday or whenever we end up having some more discussion about the pendulum. Okay, time for me. I got to eat lunch. So hope you're all doing well. Hopefully I'll see you soon. Take care.